Hello, my name is Felix Leupold. I work for the Protect and Care team for Facebook in London. And I'm here today to talk about a feature that me and some of my colleagues in London have been developing over the past year. Basically, we started a bit over a year ago when I joined Facebook. And that feature is called End-to-End Encrypted Conversations within Facebook Messenger. Who of you has used this feature themselves? By a show of hands, please. OK, well, actually quite a few. So for those of you who haven't seen it, here's a little demo of how this works. The standard use case that we advertise is, let's say you're in a bank and you want to get the bank account number of a friend of yours because you want to transfer him some money. Now, your bank account number is some very sensitive information that you might want to protect better than the regular message content that you send. So what you can do is you can start a so-called secret conversation within any other one-to-one conversation that you have in Messenger right now. And that secret conversation is going to be end-to-end encrypted. I'll talk in a bit what that means exactly. But on top of the end-to-end encryption, you can also set a timer on every message that you send, basically an ephemerality, that will say, when this timer exceeds, when this timer counts to 0, the message will be destroyed and deleted from the other person's device. So not only is the content encrypted from one device to the other, you can also have control over how long the other person has access to this. So for example, in this bank scenario case, you can send your friend your bank account information, but it will only be on his device for the next 30 minutes. Now, in my talk, I want to go into a little bit more detail about how the product works, about the user experience at first. I then want to take a bit of a deep dive into the underlying cryptographic foundation and the message exchange protocol that we use to actually encrypt and send those messages over the wire. I then want to discuss how we counter abuse, or how we fight abuse of this feature at Facebook, and then go into a bit of the technical challenges that were more on the iOS implementation side that we encountered while implementing these features. I'll leave some space for question and answers in the end, so if you could hold on to that to the end, that would be nice. First, I want to introduce my team. We're the Protect and Care team in London, and our team's mission is to make Facebook a safe space so that people can be their authentic selves. So our goal is to show people that Facebook cares about them and to make them feel protected and taken care of. And secret conversations are a particularly good fit for this motto, because with secret conversations, you have more control over the lifetime and the visibility of the content that you share. And it gives you just this extra bit of protection for the very sensitive information that you want to send to other people. Now, that doesn't mean that your regular Facebook messages are not safe or not secure. In fact, they're also encrypted. But they are encrypted only from your device to Facebook servers using TLS, transport layer encryption. Then they are stored on Facebook servers, and they are again encrypted when it's sent from Facebook servers to the recipient's device. So in the middle, there are servers, there's Facebook that has access to the content. Now, in an end-to-end encrypted world, you actually only encrypt the messages on the sender's end, and you can only decrypt it on the recipient's end. So they're encrypted from one end to the other. And that means that no intermediary has ever access to that content. So neither Facebook nor any third party can have access to your message content. And on top of that, by introducing this message timer, the ephemeral message feature, we also give you more control over how long the other person will have access to this content. So not only can you control, you're only sending it to one person, you can also control how long this one person will have access to it. Now, whenever we talk about encrypted communication, we cannot do that without introducing our two main protagonists in the classic cryptographic communication drama, which are Alice and Bob, that want to talk to each other in a secure way. If we look at the traditional Facebook Messenger model, we have something that we refer to as the account-to-account model, which means that if Alice sends a message, let's say from her iPhone, to Bob's Facebook account, it will get broadcasted to all of Bob's devices. So it will be available on his Android, it will be available on his tablet, and even on in his Chrome browser on www. Now, it will also be synced across all of Alice's devices. So even if she sent it from an iPhone, she can still read it on her iPad or on her work phone. This is very comfortable or very convenient if you can have access to your message history from all devices if you just log into your account. But it also bears some kind of security risk, because if someone gains access to Bob's account, he has access to his and Alice's complete message history. So he can read all the content, he can even impersonate Bob, And that means if Bob just uses his roommate laptop for a night maybe and forgets to log out, Bob's roommate now has a session of Bob's Facebook account and has access to all his message history and all his message content. So for secret conversations, we went from an account-to-account model to a device-to-device model. In which case, if Alice sends a message from her phone, like her iPhone, it will only get sent to exactly one of Bob's devices, and it will also not be synced across all of her devices. Now, this is great for most of our users because most people only have one mobile device, and secret conversations right now are only available on iOS and Android. But there are some users that have multiple devices, or people lose devices and want to get a new device. So the question is, how do we decide which device we actually send this message to? And the answer to that is that we have a concept of your primary secret conversation device, or your default secret conversation device. And that is, for most people, just the only phone they have. But if you have multiple phones, it's basically the first phone that you logged in with, or the first phone that you upgraded Messenger to a version that supported end-to-end encryption. Now, let's say you want to get the new iPhone 7 and you switch devices and you want to use secret conversations on that new device. How do you tell Facebook, hey, my default device changed? Well, we allow you to make any device your primary device by just starting a secret conversation from that device. And you'll see the composer is blocked in the first when you try to send a message. But if you tap that button on the bottom, you can unblock the composer and make this device primary, which will basically deregister your old device. You'll get a push notification on the old device, hey, this device is no longer your secret conversation device, and make this device your primary. Now, on the other end, on Bob's side, he will see an admin text, a little meta message telling him that you've switched devices and you're no longer talking on the same physical device as you've talked before. That gives him the opportunity to ask, hey, what's happened? Why do you have a new device? Is something going on? But it also tells him that as long as he doesn't see one of those meta messages, or in between two of those meta messages, all the history is exchanged between exactly the same two devices. So he can be sure that you are always talking from your primary phone and not somebody else has maybe stolen a session from you and is logged into your account from some random laptop that you might have used once. So this ties your identity to your primary mobile device, which a lot of people use anyways to send most of their messages. Now, for the ephemerality feature, I've showed it in the introduction video. We basically have a timer next to each message that you can send optionally for a message that you send. And that timer will count down, and if it's at 0, the message will be destroyed. Now, one fundamental question is, when do we actually start this timer? So initially we thought, well, it's easy. We just start the timer whenever you send a message. But this is quite confusing if the other person is not online in that moment. If Alice sends a message with a 10-second timer to Bob, and Bob is in the plane, it's very unlikely that he'll come online within the time frame of that message. So you'll get a push notification that he has a new disappearing message, but he'll, when he comes online, not see the message because it has already been destroyed. Now, this is first very confusing, but also frustrating on Bob's side. So we decided to not go with that approach. And it also defeats the purpose of actually controlling how long the person has access to the message, because if the person's not online, he or she can't have access to it at all. On the other hand, if we started the timer when Bob read the message, that would feel very weird for the sender side, because you're sending out some content that you're expecting to go away in 10 seconds, and the timer doesn't start, and you're wondering, how do I start the timer? 10 seconds are over. Why is the message content still there? And so what we decided to do is to stick with a hybrid approach, where we start the message timer at the send time for the sender. So whenever Alice sends a message, the timer will start on her device. But we don't start the timer on the recipient's device until the message is actually read. So the first time that Bob navigates into the thread, we'll start the timer on his end. Now that means that we can have timers that are not in sync, right? If you send a 10-second timer and Bob is in the plane, the timer will be expired on Alice's device before it has even started on Bob's device. So in this case, we're displaying what we call a tombstone message in the view of the person that has sent the message. So if Alice has sent a disappearing message that has expired, but Bob hasn't even been delivered to him yet, nor has he read it, then the message will be grayed out, showing that, okay, the content is supposed to disappear. It's kind of like you don't have access to it anymore. But it's not quite gone yet because we haven't actually sent it to Bob, so it's not really deleted yet. So to summarize the product experience, what we did is we went from an traditional account-to-account model to a device-to-device model. And we introduced ephemeral messages, which allow the sender to control how long the recipient's end has access to the content of that message. Next up, I want to talk about the message exchange protocol, about how we actually encrypt the messages that we're sending over the wire. And before I do that, I want to summarize a few requirements that we have for our message exchange protocol. So first off, since we're an instant messaging app, we want to provide asynchronous connection setup. Asynchronous connection setup means that if I want to send a message to my friend right now in that moment, I can do so without requiring my friend to be online or to do anything to set up a crypto channel with me. So the opposite of that would be a traditional phone call or a voice over IP call, where you actually have to wait for the other person to pick up before you can say anything. We also want to use a different encryption key for every message that we send. So we basically want to be better than PGP, which is reusing message keys for the message they are sending. Because if we happen to compromise a single key, if let's say a single key gets stolen or the random number generator failed or whatever, a single key is revealed, that would mean the party that has sniffed all your content would have access to the entire message history or to everything that you've sent before. So we want to use a different encryption key for each message. In particular, we want to provide two properties of encrypted or cryptographic protocols, which specify this even more. One is forward secrecy, which means that if a session key is compromised at time t, all the messages that you've sent until this point in time are still secure. All the messages that you've encrypted until this point are still secure. So from the one compromised session key, there's no way to determine previous session keys and decrypt any of your past history. And similar to that, we want to provide backward secrecy or future secrecy, which means that if a key is compromised at point t, all the messages that you'll send in the future are still secure because you cannot derive the actual message key from the future message key from the one key that you've compromised. Last but not least, we want to provide authentication, which means that you can actually verify that you do have an end-to-end encrypted channel with the participant that you're intending to have that with, and basically that you're not man-in-the-middle, so that there's no third party that actually has an end-to-end encrypted channel with you and an end-to-end encrypted channel with the person you're trying to speak with, and it's just forwarding the messages back and forth. So we want to give you a way to authenticate or to verify that your end-to-end encrypted channel is actually with the person that you're intending to have it with. Now, we didn't roll our own crypto for this. We relied on state-of-the-art industry-leading protocols, industry standard leading protocols. The protocol that we used is called the axolotl ratchet. In case you don't know what an axolotl is, it's a salamander that looks like this. This protocol is also known as the signal protocol. It's been developed by OpenWhisper Systems. And it's been primarily used in their app, the Signal messaging app, but it's also been incorporated into the WhatsApp encryption, into Facebook Messenger encryption, also in Google Allo encryption which launched a couple of weeks ago. So this is really a state-of-the-art, industry-leading it's a state-of-the-art, industry-leading crypto protocol, which we are also using in Facebook Messenger. Now, I want to talk a bit about how this protocol works in depth. But before I can do this, I have to introduce a fundamental method of bootstrapping cryptographic sessions or to derive a shared secret, which is the DiffieHellman key exchange. Now, how many of you know how DiffieHellman works or what it is? Okay, quite a few. So for those of you, you have like a 3-minute break while I go over this. And then I'll come back to how we actually encrypt the messages. So the goal of DiffieHellman is to allow two parties without any prior knowledge of each other to derive a shared secret over an insecure channel. So that means if I wanted to create a shared secret with you, for example, and we don't have any prior knowledge of each other, we don't know each other, we have no history, and we're just in this room, so everything that we exchange can be eavesdropped by the entire crowd, DiffieHellman, or the DiffieHellman key exchange, gives us a way to derive a shared secret in this environment. And the way it works is by using asymmetric key pairs. An asymmetric key pair is basically a key that consists of two parts, the public part and the private part. And as the name suggests, the public part is meant to be shared and distributed and spread to everyone in the network. But the private key is supposed to be only be accessed by you. So basically it has the assumption that the private key never leaves your device, never leaves your control. Nobody else in the network has access to the private key except for you. Now, yeah, you're sharing the public part and you're keeping the private part safe and private. Now, Diffie and Hellman have found a mathematic property or mathematic function that allows to derive the exact same mathematic value in two different ways. You can calculate, so f is this mathematic function. You can calculate the value of f by using two parameters, and it will give you the same value if you've used Alice's public part, Alice's public key, and Bob's private key. But it will give you the exact same value as if you'd used Bob's public key and Alice's private key. So if you think about this from Bob's perspective, Bob is the only person in the network that has access to his private key. And together with Alice's public key, which is something that he does have access to, that everyone has access to, he can calculate a value that is the exact same value that Alice can use with her private key, where she is the only one that has access to it, and the public key that's known to the network. So nobody else, since nobody else has access to either Alice's or Bob's private key, nobody else can derive that shared secret. Yet the only thing they've exchanged was the public part of the key. Now, the mathematics that found this are basically over exponentials and modulo arithmetic. But there is an example in the literature that explains this method by using colors and mixing colors together. And this example basically assumes that it's very easy to take two colors and mix them together and look which color comes out of it. But it's very hard to look at a mix of colors and say which two colors went into that mix. And it's also hard to say, well, this is a color mix, and I know one part that went into that color mix to basically derive the other part that went in there. So if you assume that it's easy to add colors together but hard to subtract them, we can illustrate this Diffie-Hellman key exchange by basically using just this color example. So in this color example, the private key are just randomly generated colors that Alice and Bob generate on their device, save, and never tell anybody else. So in this case, it would be red for Alice and light blue for Bob. And in order to derive their public key, they will mix their colors with something that is called a common color. Now, the common color is basically a parameter that is implemented into all the clients. So it's not something that is per user specific. It's basically the entire network knows whenever you want to do this color mix, you're going to put your private key into the common color green. So in the original Diffie-Hellman, this is basically the number that you modulo your exponentials with. An elliptic curve, it's some parameter of the curve that you're using for Diffie-Hellman. And in our color example, it will be just green. So every client in our network knows, okay, we have this common parameter, which is the color green. So Alice can derive her public key by mixing red and green. It will yield some kind of orange. And Bob can derive his public key by mixing the light blue with green, yielding some kind of dark blue. Now the two of them exchange the public keys. And now what Alice can do is she can mix her private color into Bob's public color. And what this will actually do is you're mixing red with dark blue, so it gives some kind of pink. But what happens under the hood is she will be mixing her red with his light blue and the green. So it's red, light blue, and green, which yields some kind of pink. And if Bob does the same thing on his end, what he will actually be mixing will be light blue, red, and green. So it's the exact same ingredients that went into Alice's mix at the very bottom is what goes into the mix if Bob mixes his private key and Alice's public key. So it will also yield some kind of pink, and this is what we've derived as the shared secret. Now note that whenever you have one of the public keys, even if you know the common color is green, you cannot derive the private key because we said it's very hard to subtract colors. You can't know what is blue minus green. You don't know that blue minus green is this kind of light blue. If we go back to the previous slide, basically what we are using in our implementation is elliptic curve Diffie-Hellman, and in the following I'll just use this denotion or this notation for when we do a Diffie-Hellman. But basically what I want you to take away is that we have two parties, and if you take the public key of the first party and the private key of the second party, you can derive the exact same value if you use the public key from the second party and the private key from the first party. Now we can go back to axolotl ratchet and to how we actually encrypt our messages. So the first time you log in, we have to register your device. We have to make Facebook aware that you now have a secret conversation device enabled with you. So we upload what we call a registration. In this registration, we create on your device, we create something that we call an identity key, which uniquely identifies this instance, this hardware, like this piece of device that you're using for your user. And we're uploading the public identity key, keeping the private identity key on the device. And then we also generate a bunch of these public colors that we had in the example. What we call this pre-keys. So what we are doing is we generate a bunch of seeds that can be used to initialize the first DiffieHellman. So basically on Alice's device, she's going to create a number of private colors and a number of public colors to go with that. And she's going to upload the batch of public colors up to Facebook. And this is what we call pre-keys. It's one half of the DiffieHellman that can later be used to generate the shared secret. Now she's going to hold on to all the private colors that she's generated, and then she can go offline. She can go on a plane and doesn't have to be on the network anymore. Now if Bob wants to message Alice, he can just ask Facebook, hey, give me one of Alice's public pre-keys. And then when Facebook answers, what Bob can do is he can create an ephemeral key pair on his device, which also has a public and a private part. And he will now use the public part of Alice's pre-key together with the private part of his ephemeral key pair to derive the first message key, to do the first iteration of the DiffieHellman. Now in the color scheme, the public key was the orange. The ephemeral key, we're using the private part of it, so the light cyan. And what we get is the purple, the message key, the shared secret. Now, this message key is used to encrypt the message using symmetric encryption, using AES. And then this message is sent over the wire together with an identifier of which of the, let's say, 100 pre-keys that Alice has uploaded initially we used for this particular DiffieHellman, and also the public part of the ephemeral key that Bob has created on his device. Now, since Alice still has access to the private parts of all of her pre-keys, she can now do basically the other side of the DiffieHellman, the inverse DiffieHellman, where she's using the private part of her pre-key together with the public part of Bob's ephemeral key to derive the exact same message key. So in the color example, she is using the red and the dark blue to derive that pink. Now, she can decrypt the text and she can answer, send a message back to Bob. And we said that we don't want to reuse the same message key ever again. So K1 is no good anymore. We need to generate a new message key. And the way we do this is that on Alice's side, we're generating another ephemeral key pair. Now this is called Alice's ephemeral key pair. Again, public and private part. And Alice is going to reuse the public part of Bob's ephemeral key pair from the previous message, but she's going to mix it. She's going to create a new DiffieHellman, which takes the private part of her ephemeral key pair, which she just generated, into the mix. So what she's going to get is a complete new message key, K2. Now she can again symmetrically encrypt her message with that message key, send the message over the wire, together with the public part of her ephemeral key pair. And so since Bob still has access to the private part of his ephemeral key pair, he can again do the inverse DiffieHellman using the private part of his ephemeral key pair and the public part of Alice's ephemeral key pair. Now, when Bob wants to respond back, he's going to create a new ephemeral key pair on his side. He's going to throw away the old ephemeral key pair that he has created and going to create a new one on his side. And now basically, again, it's going back and forth the same way, again using the private part of the ephemeral key pair together with the public part of Alice's ephemeral key pair, and so on. So this means that we've just described the first ratchet of the axolotl ratchet protocol. A ratchet is a tool that basically advances at every step, and the ratchet basically just symbolizes that we are never using the same message key again. And so the axolotl protocol, or the signal protocol, uses a double ratcheting system. The first ratchet is what we've just described as the DiffieHellman ratchet. So it means that whenever the message direction changes, whenever Alice answers to Bob, and then the next time Bob answers to Alice, we're basically doing a new DiffieHellman, because we're generating a new ephemeral key pair on each message direction change, and therefore creating a new DiffieHellman key, and therefore providing future secrecy and forward secrecy, because there's no way to go back and find out which key was used, 5 message exchanges ago, or will be used 5 message exchanges in the future, because it's always a new part goes into the key that is randomly generated and the previous parts are forgotten. Now, this is great for the mod, like for a message conversation where you just have answer, 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 where it's going back and forth all the time. However, that's not the reality in most communications. Sometimes, especially if one of the persons is not online, you have a bunch of messages that you send in a row. And with the just presented model, we would be using the same message key over and over again for what we call these unidirectional message sequences. So this is why we need a second ratchet. The second ratchet, which is sometimes referred to as the inner ratchet, is basically ratcheting on every message that is sent in a unidirectional message sequence. And that second ratchet is a hash-based ratchet. So instead of using the DiffieHellman key that we've derived directly, what we do instead is we use a hash of that DiffieHellman key. And basically for every message that we send, we hash the previous message key again and again and again. So the final message key is basically just a hash function to the power of n, depending on how many messages we've sent, of the latest DiffieHellman key. So for the first message, it will be the hash of the DiffieHellman key. For the second message, it will be the hash of the DiffieHellman key, and so on. So if we also include the sequence number into the message we send over the wire, the other person knows how often he has to basically perform the hash ratchet, and we already explained how they know how to perform the DiffieHellman ratchet. So the other end is able to derive that message key and decrypt every message. So this is basically how we encrypt every single message over the secure conversation channel. Next, I want to talk about how we do it with images. So let's say Alice wants to send this picture of a cute axolotl over to Bob. Now, Facebook's messaging infrastructure is very good for text messages, for rather short messages, a couple of kilobytes. It might work with image previews, or it works with image previews, but it's not really meant for large blobs, like videos or even large images. That's not what it's optimized for, and it's just not the best way to send these kind of data. So what we'll do instead is we have to upload the attachment content to Facebook's content distribution networks. And of course, since we're an end-to-end encrypted world, we don't just upload it in plain text, we encrypt it before we upload it. So we'll generate a random one-time password on Alice's device, symmetrically encrypt the content that we want to share to Bob using AES GCM. And then we basically get the URL for this content back from Facebook. And together with the one-time key that we've randomly generated, we send this information inside the secure channel, inside an encrypted packet, so that no attacker could read neither the URL nor the one-time key. So this means this message is fairly short, so it works well with our infrastructure. And on the receiving end, on Bob's device, Bob can easily just download the decrypted content from Facebook servers and then decrypt the content using the one-time key that was in the message packet. And this is basically also how we do stickers. With stickers, we basically just send the sticker ID that we want to send over in the encrypted channel, and then the receiving device will look it up in a sticker cache or fetch the sticker pack if it needs to. Last but not least, I want to talk about the authentication bit, about how we verify that, or how we allow people to verify that they actually have the right end-to-end channel set up. The way we do this is by comparing identity keys. Now, if you think back of the slide where we did the registration, I said you're uploading something that we call the public identity key. And when we do the first DiffieHellman, what we're actually doing is not just a single DiffieHellman, it's a concatenation of, I think, 4 DiffieHellmans. And one of the DiffieHellman includes the public identity key of the person that you're trying to speak to. So that means that this device that you're sending messages to can only establish a session with you if it has access to the private identity key of what Facebook has given you. Now that also means that if you go over to that person in the real world and ask him, hey, this is the public key I've been using. Is that the same public key you're using? Or is that the public key to your private key? That person can say yes, or that person can verify or deny that. And in that case, you know that you've actually set up an end-to-end encrypted channel with that specific person. So this is why we have in the advanced settings screen a tab to allow you to compare your device keys, your public identity keys. The best way to do this is in person, just see if they're actually the same, but you can also use another trusted channel like voice over IP, or if you're sure that some other messenger is you're not going to be attacked on both Facebook Messenger and some other messenger, you might also use email or some other channel to basically compare these two fingerprints. But if these two fingerprints match, you can actually, you're 100% sure there's an end-to-end encrypted channel set up to the other device. Now, if this key ever changes, we will show you what I've sent, what I've displayed earlier. We'll show you this admin text saying the other person has switched device. Because this public identity key is what defines, what uniquely identifies a device. We can notice when that changes, and we will notify you, hey, you might want to verify it again, or you might want to at least ask what happened, why this person switched devices. And in fact, we'll also fail any message that you're about to send to a device or to an account that has just switched devices. So you can see that up on this side. If you're about to send some very sensitive content, and the other person has just switched devices, we're not going to let that message go through because you didn't have a chance to actually verify that the other person's device change was legit and that no other person has maybe logged in on a mobile device and made his fake device the new primary. So we'll fail your messages in case of a device change, and we'll display these the public identity key and the advanced settings to allow you to actually verify that the public identity key fingerprints match. So to summarize this chapter, we've achieved asynchronous connection setup through the use of pre-keys. So in the registration phase, we upload a bunch of public keys to Facebook server, which can then be used for clients who want to talk to you to bootstrap an initial axolotl ratchet, an initial session. Second, we have used this double ratcheting algorithm to provide forward and future secrecy. This double ratcheting algorithm is using a new DiffieHellman key, basically on every message direction flow. And within every unidirectional sequence, it's using a hash-based function to also ratchet on the eventual message key. And then we allow to verify the other person's identity by using the hexadecimal fingerprint of his public identity key. Next, I want to talk about abuse reporting. So we are Facebook, and we have a lot of people using our products and platform, and we absolutely want no abuse of any of our features that we're building on our platform. And for secret conversations in particular, since Facebook does not have access to the message content, it's impossible for us to detect or identify bad actors within the network. So one thing that we rely on is that if any bad access or if any bad use of this happens, it actually gets reported to us. So what we built into Secret Conversation is something that's called message reporting, or we allow people to report secret conversations. If you go to the advanced settings, you can report a conversation. You can say what is reportable about it, like why is this bothering or harassing you, or what is the problem with this conversation. And then we make it very clear that in order to forward this on to our community operations that look at every report and take appropriate actions, we actually have to upload the message content to Facebook servers. So if you click that button, you will make it very clear to you that you're actually sharing part of the secret conversation with Facebook, which is originally against maybe the intention of the sender. But if the receiver cooperates with us and wants us to take at least look at it and take measurable actions, they will have the ability to share this content with us. So for abuse reporting, we also have a bunch of requirements. First of all, we don't want to break end-to-end encryption, so we want to have a certain level of the best level of confidentiality that we really one person has to cooperate with us, has to come to us and say, hey, this is something bad, I want you to take a look. And only in that case we get access to the message content. Moreover, we want to be able to authenticate every report that we get, because we want to prevent people from framing other people that they've sent them stuff which was illegal or harassing or not okay. And so we want to be able, for every report that we get, to verify that this message has actually come from the sender that you claimed it has, and has actually been going through our network, and we've actually delivered it at some point. Now, authenticity collides with another property of some cryptographic protocols, of the axolotl protocol in general, at least, which is deniability. Deniability allows you to send a message into a network and to later on deny that you've ever sent this message, that you've ever known about this message. Basically, you can just say, I've never seen this person, I've never talked to this person, I've definitely never sent this content to this person. Now, deniability is a desirable property, but we're Facebook. You already have an account with us. You have to use our infrastructure to send messages, so we can't really guarantee deniability in the first place. And for the authenticity of message verification in the report case, we do not want deniability because we want to prevent other people from framing you or from framing other people. One thing that we can provide though, is third-party deniability, which means that only if the original receiver and Facebook work together, we can actually verify that the message has been sent by you. So no other third party, other than Facebook, can determine if you've actually sent this report or if you actually sent this message, cannot determine the validity of a report. And the way this works is a method that we've developed and called franking, message franking. And the way this works is that whenever Alice sends a message to Bob, she's calculating a one-time franking tag, which is basically another key, another random key, with every message that she sends, and she's putting this into the message body that is encrypted. Now, she's also going to calculate a message authentication code, which is basically a cryptographic. It is similar to a signature. It's not the same as a signature, but it serves a similar purpose for us. It basically is a hash function that's based on the message and this one-time key that we've generated, the franking tag, and it allows you to verify that the message content has not been tampered with. Now, the MAC itself doesn't give you any information about what type of message it was, what was in the content. So it's technically a little bit like a signature, but it's not actually using your public identity or the signature crypto behind it. So it's an authentication code that Alice calculates for every message that she sends and uploads up to Facebook servers. Now, on Facebook's end, we recalculate our own message authentication code based on Alice's authentication code, and we're using a Facebook secret that only we know, that only our servers have access to. Now we're going to send the encrypted message, Alice's MAC and Facebook's MAC, down to Bob's device. And when Bob receives the message, he can decrypt the encrypted packet, and then he can recalculate the MAC that comes from Alice, because now he has access to the message content and he has access to the one-time franking key that was inside the message, and he can basically verify that the MAC that we've sent down is the same as what was in the encrypted packet. Now, if those don't match, that means something was really, really bad. Something really bad went on. Basically content was tampered with in transit, and so you will just drop the message and never display, and basically fail and never show it. However, if the two match, then he can be sure that, we can be sure that our Facebook signature was actually based on what Bob has now on his device. So when he later comes on and reports the message up to Facebook, what he will do is he will include the original message content, the one-time franking tag that was used, and Facebook's authentication code, message authentication code that we sent down. So on our service, what we then can do is we can recalculate the MAC that Alice had given this, because we now have access to the message and the tag. And since we know that Bob has verified this, we know that, okay, this must have been the MAC that was originally sent up to Facebook by Alice. And then we can recalculate which message authentication code we would have given that message if it went through our service. And if that matches the MAC that Bob has uploaded in his report, we know, okay, it actually went through our service, because otherwise we would have given it, otherwise it would not have been, he would not be able to calculate the same MAC that we would have given it when it went through our service. Now, in reality, the lower H MAC is not just using the MAC of Alice and the Facebook secret, it's also using some more meta information like the sender and the receiver, so that we can not only verify that it has been sent through Facebook servers, we can also verify that it has sent from the sender to the receiver through Facebook servers. Now, but this means that the step we can only perform if we have access to the message, access to the one-time franking tag, and access to the Facebook secret. So only if the receiver and Facebook work together, we can break deniability. No other party can break this deniability, and so we preserve third-party deniability. Last, I want to talk about some technical challenges that we've encountered while developing this feature. First and foremost, I want to talk about data storage. Now, we talked a lot about cryptographic keys and sensitive messages that you're sending. So we think that the message or the data that we generate or that we generate in secret conversations is one of the most precious data you have on your phone. So we wanted to make sure that we protect it properly. And the way we do this is, for example, for your message data, we basically store all your message data in an SQLite database that has the iOS NS file protection flag complete set on it, which means that this file is only mounted, only accessible if your phone is unlocked. So whenever you lock your phone, this database goes away, and no process has access to this data at all. Now, inside this database, we basically have a key value store for every message. It's basically a message ID, thread ID, and then we store the serialized blob of the in-memory object, basically the NS coding result of the object that we have when we process your messages. So it's a key value store with a big blob that contains your message information, and that blob is encrypted using a per-thread key. So not only is the database protected, also all the content that we store in the database is, again, symmetrically encrypted with a per-thread key. Now that per-thread key itself is protected using a master key, and that master key, together with all the other, or together with like other cryptographic keys like your private identity key, is stored in iOS keychain. So in keychain, we also use the strongest attribute on that keychain item, which is the accessibility attribute when unlocked, this device only. So this keychain item will never be backed up to iCloud and will also only be accessible when your phone is unlocked. The SQLite database, by the way, is also excluded from iCloud backup, so none of your message content is ever uploaded to Facebook. So we think that by using this approach, we're giving your data at rest really good protection. But this also means that, especially through NS file protection flag complete, we're exposing ourselves to a lot of error cases that we can run into. So we have to have very fault-tolerant access logic. Because basically, if you have a database that runs with NS file protection flag complete, the operating system can take away your resources at any point in time, especially for Facebook Messenger, where we might run background tasks when you background the app, or close, or basically lock your phone. The app will still run for a few seconds, or for a good amount of time. And if a message comes in at that point, we might check, hey, do we have access to the database? And if you've just unlocked your phone, yes, we still have access to the database, and we can start processing that message. But at some point in time, the OS decides, OK, now protected data becomes unavailable, and it's going to take away the access to the database. And basically then our read or our writes, anything might fail. We might have succeeded a few operations, but the last ones don't succeed. So basically what we had to build into this system was a very fault-tolerant logic, which was not the case in Messenger before. Basically, Messenger before was a best effort disk persistence. If anything went wrong, if you had a database inconsistency or read error, write error, you just throw away the database and download the content that you wanted to store, again, from the server. So because all your messages are backed up on Facebook servers, you don't really rely on on-client storage. It's basically, it's a best effort. It's like a cache. But in secret conversations, this is the only storage you have. It's the only place where your data is accessible. So if you lose any of your content, you have to recover from that. Otherwise, the content is gone forever. Now, with that also comes another caveat, basically the fact that the only place where we store the data is on the client, is that you have to be able to support different versions and to support migrations. So as we keep developing features for this, or improving this feature, we're upgrading our data models, we're adding structures, and we have to build infrastructure into the Messenger app that actually allows that. Because before, as I said, people would just basically throw away the legacy state and download the new state from the server. So that was definitely quite a challenge to make Messenger more aware of that the data that's stored on the client is actually very valuable and has to be kept at all times. The next thing I want to talk about is push notifications in the batch count. Since we went from an account-to-account model to a device-to-device model, we now have to send our push notifications to specific devices instead of broadcasting them to all of your devices. And we also have to take care of adjusting the batch count for every device individually. The batch count in Facebook Messenger world is the number of unread threads that you have within your top 20 threads, and your top 20 most recent threads. And that value was traditionally computed on the server and synced down to the devices using Apple push notifications. Now, with secret conversations, you might have different batch counts on different devices. Your iPad, which is not your primary device, might have 5 unread threads in your top 20 threads. But on the secret communication device, you have 3 unread secret conversations. And so your batch count there would be 8. So we had to change the infrastructure from doing the batch count calculation on the server to doing it on the client. And that was another challenge that we faced. Last, I want to talk about cross-platform compatibility. So in the traditional model, you always have the server in the middle, or the server as an intermediate, who's able to convert or transcode all the stuff that you send up and down. So in the end-to-end encrypted world, that is not possible because all your message content is serialized and sent inside this encrypted channel. So you have to make sure that Android, for example, understands the content of the message that we are sending, understands the encoding that we're using. And we also have to make sure that future versions will understand previous versions. And we also, because as we are improving this feature, we might be adding new ways to communicate or new fields to our model. And we have to make sure that our future versions are still backwards compatible. And in a way, we also have to make sure that our current versions are future compatible, that we have some way of telling you, hey, if you receive something that you cannot understand, display something like, hey, you need to upgrade your messenger, otherwise you cannot see this. And so, yeah, this cross-platform compatibility and also cross-version compatibility is something that we need to take care of a lot when the server is not in the middle anymore and it is not able to do any conversion or any anti-intermediary. So yeah, speaking of new features or speaking of improving the product, this was our first initial launch, as our first version of the product. So we're looking to evolve this over time and to make it better. And we're also looking for help to work on this. So if you're interested in the security space and also interested in the mobile space, I'd be more than happy to talk to you after this talk. As you can see, there are a lot of technical challenges involved in building end-to-end encryption into Messenger. And yeah, for those of you who haven't tried it out, I would love if you could give it a try. If you have any questions after this talk, feel free to just meet me in the hallway or shoot out an email to me. You can also talk to my colleague, Julian Krzemiński, who is basically doing the Android side of that work at Facebook. He's also here. Or you can add me on Messenger and just send me a secret conversation yourself. And now I'd like to take some questions.
Okay, at the beginning you said that in normal conversations only the part from sender to server is encrypted. So when I receive the message from Facebook server, it's not encrypted?
It's encrypted in transit. So when Facebook server sends it to your recipient device, it's also encrypted using transport layer security. But we have access to it on our servers.
Thank you. It was really awesome. I'm actually really interested in security, and I will have the last talk here about security. The question is did you have some problems with push notifications? Because Signal had problems with push notifications. And as you told about calculating badge locally, right? So basically, what is a push notification scheme you use? Do you send silent notification and then create local notification on device, or what?
Yeah, so as iOS is coming out, or as iOS is out now, I think they have a notification. They have this notification extension, which actually allows you to do the silent push notifications in a manner that is resource efficient. And yeah, so we're working towards using this. And for now, yeah, we're using what you've said basically.
Thank you. Anyone else? Okay, we have.
If you get a national security letter from the United States government, are you going to break your end-to-end encryption, or are you going to ignore the national security letter from the U.S. government?
That's a great question. That's a great question to ask an engineer that built the code for this feature. I mean, that's not my area of expertise. I wouldn't be answering that letter myself. There's a legal department within Facebook that's dealing with these kind of appeals, and yeah, I don't know what I can get you in touch with the people that work in this department if you like afterwards.
You can answer that question.
I mean, I can't. I don't know what we would do. I mean, I can get you in touch with the people that do know what we do in these cases, and they can give you an appropriate answer. But for like this talk, I'm more worried about the architectural and implementation details, and questions about that I'm more than happy to answer.
So basically, the Facebook has information about who is communicating and how much messages they transfer through Facebook servers, but they don't know the content of the information. Yes.
Yes.
And I have a question about this bunch of public keys which are sent from user device to the Facebook servers. If one of these public keys is used in message between A and B, and there is also, A is communicating with C, are there, I don't know, 100 keys are shared between these contacts, or there are just, you know, this bunch of keys is for this contact, this bunch of keys is for this contact, and so on?
No, so you have the 100 keys that you upload are for your account. So everyone that wants to talk to your account is basically assigned one of those keys by the server randomly. But the server will only use a key a single time. And basically, as soon as your device is used, the private part of it, it will also remove the private part of it. So every key is only used once. And when your key count comes to a lower level, like let's say, I'm not sure about the exact implementation, but let's say to like 20, we'll send you a top-up request, which means, hey, please upload a new 100 pre-keys to our service because we're running low on your pre-keys. And in that case, we will basically, the device will generate 100 fresh pre-keys, upload this to the server. And in every registration, we also include something that's called the last resort pre-key. So even if your device becomes offline and doesn't receive the top-up request, there's a last resort pre-key which we're able to use until that point, but that's kind of bad because we'd be reusing that last key over and over again. But if you're actually communicating, you will come online at some point and you will answer the top-up request.
Okay, so there is no way that two users of your contacts will receive the same public key and use the same public key, but because your Facebook servers are the broker, yes, for these keys.
Yeah. Facebook will only distribute a public key once.
Okay. Thank
you. I wonder if it would be possible to break that system with jailbreak somehow. Did you think about it?
So we have a threat model, and our threat model does not include jailbroken phones because keychain, like if you have a jailbroken phone, you basically circumvent all the. So that goes for the on-device storage. Sorry to like make that perfectly clear. The signal or the message exchange protocol. It doesn't matter if your device is jailbroken or not. What you risk when your device is jailbroken is that your data is not protected stored at rest anymore. Because basically any process can now access your keychain, no matter of like any of the iOS specific flags or properties that we set on it. So you're losing all your protection, all your data protection at rest, but you still have the end-to-end encrypted channel. There's no other third party can defer anything from the intercepted traffic or can break that level of end-to-end encryption.
Any more questions?
I have a question about device-to-device encryption. How do you identify the current device? For example, it's a very stupid example, but for example, Alice can write a question to Bob and reinstall application, and she will never get answer to her question.
Right. So the way we identify a device is the identity key. So as soon as you generate a new identity key, you have a new device, a new identity for that matter.
This is the same device.
It is, yeah. So basically, the identity key is stored in keychain, and the way that keychain works, at least at the moment, is that it survives new install, like it survives an uninstall and a reinstall. I think at least if other apps are still installed. I'm not so sure. Like Apple doesn't really disclose much information about how long the keychain item will live, but at least in practice, now when you uninstall Messenger and you reinstall it, it will still find the old keychain item. So it will reuse the old identity key. However, all your message history will be gone because the database was deleted when you actually uninstalled the phone, of course. But that means if you uninstall and reinstall, it might use the same identity key again. But if you, for example, switch to a new device and even recover it from backup, since those keys are never backed up, you will have your phone will basically check, do I have an identity key to use? Won't find any. In that case, it will regenerate an identity key, and that means for Facebook servers, oh, there's a new device. So if you're able to delete, like if your identity key is lost or gone on the device, the next time we start up, we're going to re-register you, and it's going to look for Facebook servers, and to all of your recipients, it's going to look as if it was a new device.
Okay, thank you.
Any more questions? I have one question. If someone uses man-in-the-middle attack, my messages are still secure or not?
Wow, this is a how can you specify the man-in-the-middle attack a bit more?
I don't know. Just
I mean,
someone that can break a connection between, for example, Alice and Facebook server, and for Alice, this man in the middle will be a Bob, and for Bob, this man in the middle will be Alice.
okay, so we have some extra layers of protection for preventing man-in-the-middle attacks on our regular transport layers. So we do certificate pinning, so that it's very hard for a client, basically a non-compromised client, to accept a transport link with a fake Facebook server.
Okay.
So that's very hard to do. If you're able, if you're able to perform a man-in-the-middle attack, then the person who's the man-in-the-middle will have access to the messages. But I think it's in practice, it's pretty hard.
Yes. Okay. Thank you.
Sorry, and a little more question about identity key in keychain. So it's possible to get this key from original device, make a copy of installation, for example, on another device, and someone else, the third party, can get answer to the question.
So the good thing about this axolotl ratchet is that it's actually like the key state, the state that's used to actually encrypt the messages, is a lot more than just your identity key. Your identity key is one part to it. And also, the item that we store in keychain is actually protected once more with your Facebook login. So if you log out of Facebook, we'll also basically there's another key that is this information is encrypted with, which is stored, like one half of this is stored on Facebook servers and the other half is stored on your device. So if you log out of Facebook, you will be unable to recover the content that you have in your secure messaging database, or the key material that you have. And in that case, the data is useless, cryptographically useless at the same as well. However, if you're still logged in and somebody takes an exact copy of your device memory and your device storage and puts this into another device, then yes, he basically cloned your device, so he would be able to impersonate you.
Thank you.
Cool. It's 2 minutes left. Are we having lunch now?
Yes.
Cool.
Now it's a break for lunch.
Okay. So should we just go to lunch then? If there's no more questions, I don't want to interrupt any. If there's no more technical questions. I'm hungry. Oh, there's one more. Okay.
At the first presentation today, there was an information that Facebook for iOS has 80,000 classes. So how big is Messenger for iOS?
Wow. I don't know that. I don't know that off the top of my head. Because we have a very modularized way of implementing things at Facebook. So we have a service architecture. So the secret conversation is actually a service that we've pretty much developed separate from the main app. It was actually, when we tested it, was integrated into a standalone app. And then we have a very well-defined interface that communicates with the main Messenger app. And the main Messenger people actually sit in California, and we've worked closely together with them, but we don't. It's not that I actually, know the size of the Messenger app out of the top of my head. It's a sizable app, but yeah. Cool. Thank you very much.